It's electric! Hello science fans, Bill Nye here. Today we are embarking on an electrifying adventure, quite literally. We are going to build our very own electric motor. Electric motors power everything from your mom's food blender to the toys you play with, and even the enormous machines that build our cities. With just a battery, some wire, a magnet, and a couple of paper clips, you're going to create something that all by itself, powered by the wonders of science. This isn't just a craft project, it's a hands-on exploration into the fundamental principles of physics, specifically electromagnetism. So, roll up your sleeves, get your thinking caps on, and prepare to be amazed by what you can achieve. We'll go step by step, so don't you worry if you think this sounds complicated. Let's get started on this amazing project and build something truly spectacular. Science rules. Alright, future engineers and scientists, before we can start building our magnificent motor, we need to gather our essential supplies. First up, you'll need some insulated copper wire. About 1 meter of 0.6 millimeters to 1 millimeter diameter enameled copper wire is perfect. Next on our list is a power source. For this, a simple D-cell battery, one of those chunky ones, will do the trick splendidly. Alongside the battery, you'll need a couple of large metal paper clips. Not the tiny plastic-coated ones, but good, sturdy metal ones. Of course, what's a motor without a magnet? You'll need a small, strong magnet. A neodymium magnet, sometimes called a rare earth magnet, is ideal because they pack a powerful magnetic punch for their size. Finally, you might want a few extra bits to make life easier. Perhaps a small piece of sandpaper for preparing the wire ends, and a cylindrical object like a thick marker pen or the D-cell battery itself to help you wind your coil neatly. Having all your materials laid out and ready to go is the first step to a successful experiment. So gather your gizmos and let's move on to the construction phase. Now for the really hands-on part, where we start to bring our motor components into existence. Our first task is to create the heart of our motor, the coil or armature. Take your enameled copper wire, that shiny coated conductor. Wrap this wire around a cylindrical object to create a neat coil. Leave about 5 centimeters of wire sticking out at each end. Wrap the wire around your cylinder 15 to 20 times. Carefully slide the coil off the cylinder. Loop the wire ends around the sides of the coil. Now prepare the wire ends. Remove all the enamel insulation from one wire end. For the other end, remove the enamel from only one side. This half-scraped end acts like a switch, crucial for continuous motion. With our coil expertly wound, it's time to build the stand, or the power pedestal, for our motor. Take your 2 large paper clips. Bend them to hold our coil and connect to the battery. Straighten the longer part, leaving the inner loop intact. Create an L shape with a loop at the top. The straightened part connects to the battery, and the loop cradles the coil. Ensure the loops are large enough for the coil to spin freely. Now let's introduce our power source, the D-cell battery. Place the battery on a flat, non-metallic surface. Attach the paperclip supports to the battery ends. Use tape or rubber bands to secure the paper clips to the battery terminals. Ensure a solid electrical connection. The paper clips should be upright and parallel with aligned loops. This framework is the backbone of our electric motor, ready to channel the battery's energy. Section 5. The Grand Assembly. Bringing your motor to life. The moment of truth is approaching. We have our beautifully wound coil with its specially prepared ends, and we have our sturdy power pedestal made from paper clips and a battery. Carefully take your copper coil. Gently place the ends of the coil's wire tails into the small loops at the top of your paper clip supports. The coil should now be suspended between the 2 paper clips, able to rotate freely. Make sure it's balanced as well as possible. If it's lopsided, it might struggle to spin. Now for the final crucial component, the magnet. Take your strong neodymium magnet and place it on the battery, directly underneath the center of the copper coil. The magnetic field from this magnet needs to interact with the coil. With the coil resting in the paperclip cradles and the magnet in position beneath it, your motor is fully assembled. At this point, nothing might be happening yet, or it might give a little twitch. Sometimes, it needs a little nudge to get started. The current is now flowing from the battery through one paperclip into your coil, and then out through the other paperclip and back to the battery. Section 6. The Invisible Dance. How Electromagnetism Makes It Spin. So what's the secret? How does this collection of wire, paperclips, and a magnet actually start to spin? It's all down to a wonderful phenomenon called electromagnetism. Science is cool. When you connect the coil to the battery via the paperclips, an electric current starts to flow through the copper wire. As these electrons zoom through the wire, they create something amazing, a magnetic field around the wire. Because your wire is wound into a coil, the magnetic fields from each loop of wire add up, creating a stronger, more concentrated magnetic field. This effectively turns your coil of wire into a temporary magnet, an electromagnet, whenever current is flowing through it. Now, you have two magnets in your setup, the permanent magnet sitting under the coil, and the electromagnet that your coil becomes when the current flows. And what do magnets do when they are near each other? They interact. They push and pull on each other. The clever part is how these forces make the coil rotate continuously. The magnetic field of your coil will try to align itself with the magnetic field of the permanent magnet. Section 7. Force is with you. Understanding the push and pull. Let's delve a little deeper into the forces at play. The specific force that makes our coil move is called the Lorentz force. It's a fundamental principle in physics. The Lorentz force acts on a current-carrying wire when it's placed in an external magnetic field. In our motor, the current is flowing through the copper coil, and the external magnetic field is provided by our permanent magnet. This force is always perpendicular to both the direction of the current and the direction of the magnetic field. So, as current flows through one side of the coil that's passing through the permanent magnet's field, it experiences a push upwards. At the same time, the current on the other side of the coil is flowing in the opposite direction, so it experiences a push downwards. These two opposing pushes, one up on one side and one down on the other, create a twisting force or torque on the coil. This torque is what makes the coil start to rotate. Section 8. Behold, the whirling wonder. Visualizing the spin in fields. If your motor hasn't started spinning on its own yet, give the coil a gentle flick in one direction. Sometimes it needs a little encouragement to overcome initial friction and find its rhythm. Once it starts, watch it go. It might be a bit wobbly at first, a bit hesitant, but then it should settle into a steady spin. Isn't that just amazing? You've created motion from electricity and magnetism. Observe how the shiny copper coil whirls around, a blur of motion powered by invisible forces. Let's try to visualize those invisible magnetic fields we've been talking about. Imagine the permanent magnet on your battery. It has a north pole and a south pole. Invisible lines of magnetic force loop out from its north pole and curve around into its south pole, passing right through the area where your coil is spinning. Now picture your coil. When current flows through it, it also generates its own magnetic field, with lines looping through the center of the coil and around its sides, creating its own north and south poles. As the coil spins, its magnetic field is constantly interacting with the fixed magnetic field of the permanent magnet. It's a dynamic, ever-changing interaction. Section 9. You've done it! Now what? Motors, missions, and more. Congratulations, super scientist! You have successfully built your very own electric motor. Take a moment to appreciate your creation. You've taken simple, everyday materials and using the principles of electromagnetism, you've made something that moves. Electric motors are everywhere. Think about it. Fans that cool us, electric toothbrushes, drills, washing machines, electric cars, trains, and even tiny motors that make your phone vibrate. They all work on similar principles to the little motor you just built, though they are, of course, much more complex and powerful. Now that you're a motor building expert, why stop here? The world of science is all about experimentation and asking what if? What happens if you use a stronger magnet, or two magnets? What if you change the number of turns in your coil? Try making a coil with more turns or fewer turns and see how it affects the speed or power of your motor. This project is just the beginning. So, go forth and continue your scientific adventures. Bill Nye signing off. Keep experimenting.